Assalamualaikum warahmatullahi wabarakatuh and good afternoon. My name is Siti Rohida binti Muhammad. I'm from University Malaysia Pahang. Today I would like to present my paper to IPCME 2020 with the title of Investigation of Design Space in Manufacturing Meta-Biomaterials by Additive Manufacturing. My presentation will be include introduction, methodology, result and discussion and conclusion. Meta-materials are known as a unique class of materials usually construct in repeating pattern that exhibit unprecedented combination of mechanical, mass transport and biological properties made from biomaterials. Meta-materials has been studied in this paper for the porous orthopedic implant application made from metallic biomaterials in order to tailor the elastic modulus of the materials and to promote the bone tissue regeneration between the implant and bone tissue. And the major factor of the unit cell shape, unit size, geometry, and the orientation and arrangement of the unit cell become the main factors that affect the homogeneous manner of metamaterials. Okay, from the problem statement, there is difficulty to determine suitable range of design variable of metamaterials for bone implants. The various unit cells from the previous study are focused on manufacturable only, and the best topology need to determine for tailoring solid properties of materials. There is approximately 200 gigapascal match to bone properties is range from 1 to 30 gigapascal. Objective of this paper is first to present a systematic approach to determine the optimum topological parameter of meta-biomaterials for orthopedic implant, and second is to investigate the design space mapping in manufacturing meta-biomaterials and to comprehend the relationship of with geometrical constraint inflicted by biological necessities, mechanical requirement and additive manufacturing. Methodologies. First is development of cell topology design domain, where in this paper have two different unit cell, namely square and diamond unit cell. This unit cell have generated with the solid world, and the porosity can be calculated from this equation. And second is development of design space. Before we generate this design space mapping, there is two important requirements need to be considered. First is biological requirement, where the pore size range from 50 until 1000 micrometer with porosity more than 50%. And these boundaries are represented in y-axis and isometric line. And second one is manufacturing constraint, where the additive manufacturing technology is restricted to manufacture a minimal strut thickness bigger than 200 micrometer, and the constraint value is illustrated in x-axis. Okay, the area of the interest that generated in the both design space is to become the area where the sample will be selected in this paper. Okay, table 1 is summarize the geometrical details of the representative sample, where the diamond have 7 samples and the square have 6 samples. Unit cell size for the diamond is range from 1.5 until 2 millimeter, and 1.0 until 1.5 millimeter for the square, and the strut thickness is range from 0.3 until 0.7 millimeter for both diamond and square unit cell type, and the porosity are ranging for the diamond from 0.56 until 1.1 millimeter, and the 0.5 until 1.0 millimeter for the square, and the porosity is range from 58 until 82% for diamond and 50% until 70% for the square unit cell type. Okay, materials used in this paper is a cobalt chromium molybdenum powder, where this average powder particle size is 22 micrometer and the powder shape is spherical. Okay, fabrication process that involved in this paper is selective laser melting. This is one of additive manufacturing technology with the energy density of 190 joule per millimeter cubic, where the energy density can be calculated from the process parameter that summarized in table 4, including laser power, laser scan speed, head spacing, layer thickness, and also the chamber environment. Okay, for the morphology evaluation, there is morphology and manufacturability testing, and also dimensional accuracy that evaluated by optical microscope. Okay, this prediction for effective elastic modulus with two approach. First is Gibson and SB model that is calculated with the equation based on the porosity of the sample. Second one is the finite element analysis from the ANSYS software for the quasi-static testing. With the sample has been meshed into 4 node tetrahedral element with the 0.1 mm element size and displacement 0.1 mm on top surface and also fixed at the bottom of the. Okay, for discussion, Table 2 summarize the manufacturability of Meta-Biomaterials that can evaluated for the strut thickness and the pore size, and the result of them as manufactured samples are compared with the original CAD design for the both samples. Okay, from the table, for diamond unit cell type, the average strut thickness error is 30% and average error of pore size is 1.8%. This is a good result because of the inclination angle of diamond, which make layers between two adjacent layer can support the next layer during manufacturing process, known as self-support feature. However, at the smaller unit cell size, there may result in lost connectivity between adjacent cell or strut is too thin to be manufactured by SLM process. For the square samples, the average strut thickness error is 21% and average error of pore size is 1.4%. The overhang phenomena on the square types and more partially melted powder attachment expand the size of the strut features of the square, and the manufacturing error was susceptible to the strut thickness that close to the manufacturing limits at high porosity percentage. From the effective elastic modulus for the Gibson SB and finite element analysis, by Gibson SB method, effective elastic modulus of diamond type ranging from 6.5 until 44 gigapascal, while 18 gigapascal to 50 gigapascal for the square. The elastic modulus for higher volume porosity will make a good agreement as the values closer to the human bone properties from 1 until 30 gigapascal, except for D3, D4, S3 and S6. From finite element, the effective elastic modulus of diamond type ranging from 3.01 gigapascal until 4.79 gigapascal, while square ranging from 6.34 to 28.75 gigapascal. Most of samples are in the range of cancellous bone properties, except for S3, S5, and X6 that exhibit elastic modulus similar to cortical bone properties with elastic modulus of 50 until 30 gigapascal. Okay, this deformation mechanism that get from the finite element analysis for the both sample, deformation commences from the top and then the structure collapses by each layer by the cell continuously. The homogeneity of failure mechanism indicated the potential of high impact resistance from the strut of the sample. Okay, for the square unit cell, there's buckling microstrut predicted to result in high energy releasing at respectively failure stage, since the strut able to endure axial distortion due to their equivalent direction. For the diamond, failure of diamond type structures followed by shearing of the microscale strut lead the structure to collapse as bending deformation, where strut crush the center of plates contribute to a continuous shear fracture in 45 degrees. For the conclusion, this paper presents two distinct meta-biomaterials of orthopedic implants and proposed a method to optimum topological constraint in terms of biological and mechanical properties, requirement, and additive manufacturing limitation. The geometries discrepancy between design models and manufactured sample obtain percentage of error of 30% for diamond structure and 21% for square structure. The proposed technique yield average error reduced to 70% for diamond structure and 44% for square structure of effective elastic modulus from theoretical calculation. This is a reference for this paper from me. Thank you.